Hello everyone, today I'll be discussing with you the vibrational analysis of the Cessna 172's wings. The Cessna 172 is one of the most popular light aviation aircraft used in the industry, hence ensuring the aircraft's wings are adequately equipped to handle aeroelastic flutter is of utmost importance. Aeroelastic flutter occurs when the wings reach resonant frequencies. Originally, the wings of this aircraft are a modified NACA 2412. However, for this report, we'll just assume that it's a normal NACA 2412, as seen here. For this analysis, I've assumed the wings to be a fixed cantilever beam, similar to this ruler here. So, one of the sides will be fixed, the other will be free to deflect around. This will be critical in finding the resonant frequencies. The meshing and the results, including the nodal analysis and the harmonic analysis, will be discussed in the answers section. The results were verified using a H convergence study, as seen here. The study was used to find the optimum mesh size. For this report, the size was chosen to be 0.06 meters. The convergence study indicated that all the data points converged to a single value, ultimately verifying the analysis.
For this section, I'm going to be looking at the answers. Here we can see the geometry of the plane wing. As we rotate around, we can see the uniform body and the NACA 2412 shape. The material used for this, as indicated, is the aluminium alloy. Now looking at the meshing, fortunately the mesh is not as ideal as it could be, as the most ideal mesh would have squares. However, looking at our H convergence graph from before, the triangular mesh works just as well as the square one. Also indicated by the H convergence graph, we can see the element size for this mesh is 0.06 meters. Groth size is 1.8 and the max size is 0.12 meters. Since we're assuming the wing is a fixed cantilever beam, there is a fixed support on one of the edges of the wing. Total deformations can be seen in this section. They are all animated to show a better look of how they would act in the real world resonant frequencies. The red indicates the max, while the blue is 0 and is a minimum deflection. We will go through each mode shape to gain a better understanding. The frequency for the first mode was 4.9, followed by 30.3, 37.5, 39.3, 83.1 and 117.6. As we can see, the resonant frequency causes the aircraft wings to move and deflect in completely different variations. We will be now looking at the harmonic response. The analysis settings were set to linear and the range maximum of 2000 Hz with 200 solution intervals. There is a uniform pressure normal to the surface being applied. The magnitude of this pressure is 57.2 kilopascals or 57,200 pascals as shown. Finally, we can look at the solution to the harmonic response. In this case, we used the frequency response deflection. As indicated in the graph, the maximum amplitude was 2.26 millimeters. Thank you so much for watching my video. If you have any questions or want more clarification, feel free to comment below. Thanks everyone.